All right, so now comes the fun slash hard part. So what we need to do is expand that integral, which contains all of the physics of the problem, to figure out how thermal conductivity depends on things like temperature and mass and scattering cross section. So let's write it out again. I'm just rewriting it here, copying the solution. The temperature derivative of the equilibrium distribution can be calculated, and I'll just write, I had it on the previous page and I'll just write it back out again. And the scattering time itself depends on the velocity, because the mean free path is 1 over eta times the scattering cross section, but then because it's a rate, that also involves the velocity. So if we take all that stuff and we plug it into the integral, we can expand that out with some amount of pain. It takes a couple of seconds to do this. What I'm going to recognize is that in order to actually do this integral, first it makes sense to actually switch it to cylindrical coordinate or spherical coordinates. So instead of doing Vx, Vy, Vz, we'll do V, phi, and theta. And then after a little bit of cancellation, I can write that out in spherical coordinates. I'll notice that v sub z, with like the velocity in the z direction, can be written, or at least the square of it can be written as v squared cosine phi, and then I'll just write out the rest of it. And then that means that there'll be two other integrals other than the v integral that I'll be able to do right away. So one of them involves cosine squared of phi on sine phi d phi, and the other one involves theta. I'll be able to do both those integrals right away. One of them is 2 pi and the other one turns out to be 2/3. Now comes the hard part. So if I look at the topmost integral that I couldn't do, that involves an integral that has a bunch of terms with v in it. Obviously, if I look at the exponential term, or the Gaussian term, it doesn't contain just v. It has half mv squared over kbt. And so what I need to do in order to make that look like an easy to do integral is group terms such that they look like a change of variable, such that I collect everything with like a half mv squared over kbt together and do a substitution of variable. I'll call it xi. So that's what I'm going to do now. All right, let's do the easy part of that first. So we'll be able to identify a couple of out of place constants. So I can pull the 2/3 from the bottom integral and the 2 pi from the bottom integral out. If I look up in the upper equation, there's also an out of place pi up there that I can pull out. You'll see, or sorry, a pi to the 3/2 that you can pull out. And then let's see, is there anything else up there I can do? Yeah, what I'll do is I'll pull out, there's a half m that I'll sort of group towards the beginning. And I'll look for some other things that I can group with it. I'm trying to make a term that looks like half mv squared over kbt. So I'll see an extra t sitting around on the left side, but there's no kb, so I'll just multiply and divide by kb to make that term. There doesn't appear to be much I can do about the matching term to go with dv. I can pull out the scattering cross section. What else can I do? Doesn't appear to be much else to do, so I guess what I'll do is I'll just keep going. So I'll pull the v, there's a v squared and a v sitting around. I'll put those together as a v cubed, and then conveniently sitting right to directly to the right of that is a m to the 3/2 over 2 kbt to the 3/2, which is sort of the matching dimensional term. And then the last term there is mv squared over 2 kbt, and then the very last term is the Gaussian that I was looking for. There's one unmatched term, the dv. I still don't have an m over 2 kbt to go with that. So what I'll do is I'll just put it there, multiplied by a factor of half, and then I'll have to divide by the same thing and take it outside the integral. Whew. Okay, so that gives me all the matched dimensional terms, and I'll identify all of the little xi's that are sitting around. I think if you count them up, you'll see that there are 7 of them together, along with the exponential term. So let's take that and write it all back out in one fell swoop. So, okay, let's write that all back out. So that was a 2/3 times 2 pi divided by pi to the 3/2 times kb, 2 kbt over m to the 1/2 power There's a scattering cross-section, and then there's our integral that involves xi to the 7th power e to the minus xi. All right, so that integral turns out to be equal to 3. Thank goodness it has sort of an easy-looking result. So the 3 cancels with the other 3. And then all that's left to do is actually collect all of the things together and make sure we're not double counting. So there's, I guess, 2 to the power 5/2. It looks like the pi is to the 1/2 power. A kb over, there's a kb to the 3/2 power times t to the half over scattering cross-section and an m to the half. Whew. Okay, so if I take a really close look at that, what you'll see is that the back factors, the kb to the 3/2, t to the half over sigma to the m to the 1/2 power, that is exactly the same as what we got in the much, much simpler version of this theory. And the only thing that's different is really the prefactor is a little bit different than what we got earlier in the class with the simplified transport theory.